Okay, we're going to do a review for exam 7 on chapter 9. And I'm working from the handout that I gave you in class. This is version 2 review. So let's get started with the ones I've highlighted. Get this up out of the way so I can see what I'm doing. Okay. Which of the following molecules contains a central atom with sp2 hybridization? All right. So there's one. And remember, when we talk about groups, we could have say 2, 3, 4, 5, and 6. And the electronic geometry. Right? So this would always be linear. And the hybridization would be SP. 3 would be trigonal planar with SP2. 4 would be tetrahedral with SP3. Might as well finish them. This is trigonal bipyramid with DSP3, and 6 would be octahedral with D2SP3. So the simplest way to approach this, since the Lewis dot structures are given to you, then all you have to do is just count the groups. And if we look at A, I'm not going to draw these up here because I don't have time. If we look at A, it has 2 central atoms, aluminum and phosphorus. And if we look at each one in turn, aluminum has 4 groups, phosphorus has 4 groups, and there are no lone pairs, so we just count the bonds. So those would have 4 and 4, those would be tetrahedral, right? It doesn't work. That's not sp2, it's sp3. Then if we go to B, where we have boron as the central atom and fluorine around it, the boron only has 3 groups, right? It is deficient in its octet, but it still only has 3 groups, which means sp2. Right? There's your answer. But if we were to look at the rest of them, you see the central atom for C has 3 bonds and 1 lone pair. So it has 4 groups. And the nitrogens of hydrazine, right, so this one won't work. And the nitrogens for hydrazine, each one of those has 3 bonds and 1 lone pair. So that's 4 groups. Right? So that one won't work, just like A. And the last one only has 2 groups around the beryllium. It is really deficient in its octet. But 2 groups only means linear, right? So that's sp hybridized. Okay, that's number 1. So we found our answer, that's B. And let's go to 3. I'm going to leave this up here just in case. And start working over here. Okay. Consider the molecule and the following hybridization choices. What is the hybridization of the carbon atom that is double bonded to oxygen? All right, so what we've got to do here is to locate any lone pairs, because we're not given the any lone pairs in there, and the possibility is such that there may be some. So let's see, we have 4 carbons. All right, 2, 3, 4, and then a triple bond to a nitrogen. Then we have a chlorine here and a hydrogen here. And there's our double bonded oxygen carbon. And then, wait a minute. Oops. I'm off by one. This is the one with chlorine, and this is the one with oxygen. And then this one has 3 hydrogens. Okay. So if we just focus on this one, carbons typically have 4 bonds to them. Sometimes they can have lone pairs, but usually 4 bonds. And this one does have 1, 2, 3, 4. It has 4 bonds, but 3 groups. So that means the carbon has to be sp2 hybridized. And if we're looking for any others, this carbon has 4. This carbon has 4. This carbon has 1, 2, 3, 4. Doesn't need that. Now this wasn't part of the question, but how about that nitrogen? All right, that nitrogen has a lone pair right there. That's so the nitrogen can have its octet. Now, if we go to the Lewis dot structure, we'll find that we had to put a lone pair there. In fact, when we first started, the procedure for the Lewis dot structure, we would have a bond here, and then 3 pairs there. And then we would use 2 of those pairs to make those double bonds, double and triple bond. So that nitrogen has a lone pair. But that carbon is sp2 hybridized. Let's see, consider, I didn't mark for hybridization of the nitrogen atom while we're here. Hybridization on the nitrogen atom has to be sp, 1, 2 groups. Right. Okay. Oh, this is a different molecule. Okay, we're going to number 5. Hold this just right, or it gives me a thin line. Okay, 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons and a nitrogen atom. And that one is like that. And I'm gonna put the lone pair there while I'm here. Another thing about when we write, one of the conventions for writing organic compounds is, if I haven't said this before, is when we write hydrogens, they're bound to the carbon they're closest to. So if we have a double bond here and we have a hydrogen there and then another bond, that hydrogen belongs to this carbon. It's not a hydrogen bound to that carbon. It can't be really, because hydrogen can only have 1 bond, right? So if you tried to connect this hydrogen to those in between those 2 carbons, it wouldn't work. So by convention, that hydrogen is attached to this carbon. And then let's see, this one is double bonded oxygen, single. This one has 2 hydrogens like that. Okay. While we're at it, I forgot, I left those out. That oxygen has 2 lone pairs. Each one of these there's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4, and then it's octet. So everybody's accounted for, and we numbered the carbons from left to right. Okay, now we want to do the hybridization on each one of the carbons. All right, so this one has 1, 2, 3 groups. I'll put them up here. 3 groups means sp2. This one has 1, 2, 3 groups. That one is also sp2. This carbon has 1, 2, 3 groups. It's sp2. This one has 1, 2, 3, 4. That has 4 groups. It's sp3. This one has 2 groups. Right? So it's sp. And it didn't ask for nitrogen, did it? Okay. So 2, 2, 2, 3, and 1. That's A. All right. Got that? Okay. So let's go to 6. The hybridization of selenium in selenium hexafluoride. I'm going to do this one from scratch. We know that compound is right. It's given to us. It's identified. I mean, somebody determined that the ratio, the molecular ratio, was 1 selenium for every 6 fluorines. So that's the molecular formula. Now we want to determine its hybridization. So we've got to go all the way through the Lewis dot structure. Selenium would be in the oxygen sulfur group, so it would be 6 valence electrons. 6 times 7 is 42. So we have 48 valence electrons. Selenium in the middle. Make room for 6 fluorines. Now the temptation is to say, okay, 6 groups octahedral, D2sp3. And that may be right, but we can't say for sure until we've used up all of our electrons. So 2, 4, 6, 8, 10, 12. Minus 12 is 36. 2, 4, 6. 6 times 6 would use up all of those. So in fact, we do have 6 groups around the selenium, which means D2sp3 hybridized. That would be E. Okay. Moving on, number 9. Okay. Pi bond is the result of. So how do we get a pi bond? And I assume we're still in the valence bond theory discussion. We get pi bond by overlapping unused p orbitals. So if we do have to do some hybridizing, we got to have some p orbitals left over that aren't hybridized in order to get them to form our pi bonds. So sideways overlap of 2 parallel p orbitals seems to be the best answer. Pi bonds are always off axis, whereas sigma bonds are on axis. That makes pi bonds a little bit weaker than sigma bonds, because there's some strain in the in what they have to do to overlap. And that, I guess that you could conceive that as another problem for the valence bond theory. Right? How do you get those orbitals to bend? Who knows? Okay. 11. Let's do 10 and 11 since they're using the same 6 carbon structures. All right, so we've got this one. And we've got, see, which ones do we want here? This one and this one. And we've got another 6-carbon structure. Just that. Okay, and that's another peculiarity about organic chemistry. It can get so complicated with carbons and hydrogens all over the place. We don't write the carbons and we don't write the hydrogens. We just understand that anywhere these two lines intersect, those bonds, there's a carbon there. And we put in hydrogens where they're needed. So, like I said before, we assume that carbons prefer 4 bonds. So if this carbon only has 1, 2, 3 attached to it, that means there has to be a hydrogen. We just don't write the hydrogens in to keep you from getting too messy. Okay, so the question for 10 is, which molecules have p orbitals that share an electron pair to create pi bonds? And the matter of fact, it's all of them, right? Because we've got 1, 2, 3 there, we've got 2 there, and we've got 1 there. So all 3 structures overlap p orbitals. It's just that this one overlaps more than that one, and that one more than this one. So for 11, which molecules have equivalent carbon-carbon bonds throughout the molecule? Okay. For this one, we have single, 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 and 1 double. So ideally, these 5 are equivalent, but not to that one. There's some strain in this molecule. And this one, these 2 are similar, but these other 4 are similar to each other, but not similar to the others. This one is a special case. Remember, this is benzene. And it's written like this, but in fact, it looks like closer to this. Because these alternating pi sigma bonds do what we call delocalize. They delocalize the electron density so that the entire molecule is symmetrical with respect to the length of those bonds. Every bond in this molecule is the same length and the same strength. That's what gives it extra stability. So the only one that has equivalent carbon-carbon bonds throughout the molecule is this one. That comes under the topic of aromatics. If you stumble into organic course. All right, number 12. Okay, it looks like we're getting into molecular orbitals here. The electronic configuration of a particular diatomic species is that. What is the bond order of this species? Okay. Rather than draw that up there, we just find what bond order is, right? Bond order calculation equals the number of bonding electrons minus the number of anti-bonding divided by 2. So in this case, the bondings are the ones without the asterisks. So if we look at from the left, we find we have 2 electrons in the sigma 2s. We have 2 electrons in the sigma 2p. So that's 2 plus 2 is 4. And we have 4 in the pi 2p. And that's all the bonding electrons. 4 plus 2 plus 2 is 8. Okay, how about the ones with the stars on them? The first one with a star is the sigma star 2s, has 2 electrons. And the other one that has 2 electrons in the pi star 2p. So that's 4. So we have 4 anti-bonding electrons. 4 from 8 is 4, divided by 2 is 2. So the bond order is 2. Okay. All right. The other thing that we didn't mention in lecture, it just occurred to me. When we're in the valence bond theory and we're talking about sigma bonds and pi bonds, and we have to have whole numbers, right? Single bonds, double bonds, triple bonds. I've never gone any higher than that. In that discussion, we're saying that's the bond between two atoms. But when we calculate bond order, that's for the whole molecule, and no matter how big it is. So that's another difference in calculating the stability of a molecular orbital model versus the other model. Valence bond theory, localized electron model. 13. As the bond order of a bond increases, okay. So we're saying the bond order increases. What else happens? The bond energy, something, and the bond length, something. As the bond order increases, the bond energy also increases. And the bond length, if we're just talking about the very simplest molecules, then we can say something about the bond length. The bond lengths are going to vary in large molecules, even though we calculate a certain bond order for them. But in general, the bond length would decrease. So bond energy goes up, bond length goes down. And when we say bond energy, that means how much energy do you have to put in, so it's a positive value, to break the bond. And if the bond is more stable, shorter and more stable, it takes more energy to get it apart. So that's why the bond energy is higher, the bond length is shorter, which would be C. All right. 15. How many unpaired electrons in F2 ion are based on molecular orbital theory? How many unpaired electrons? That's not worded right. I think what we're trying to say is how many unpaired electrons are there in the F2 ion based on the molecular orbital theory? That it just doesn't it doesn't flow properly. So if we're given this molecular orbital sequence here for F2 with a 2 plus, and we have let's see, no mixing. That makes sense. Okay, so we have sigma 2s, we have a sigma star 2s, and we're leaving off the 1s. So we're just involved, we're using my mind's gone blank. It happens. I2p, I star 2p, and sigma star 2p. Valence electrons. You guys are supposed to help me remember these things. Okay, so how many valence electrons are we talking about here? Well, if it were neutral, we would have 7 times 2, so 14. But we've got a 2 plus ions, so we have to subtract 2 of them. So we really only have 12 electrons to deal with. Okay, so we're going to use the alpha dot principle and throw them in here. 2, 2, right? Sigmas can only have 2, 2. This one can have 4. See how many we used? We've used 10 so far. So we can put 2 more in this one. There we go. We don't need the last one. So how many unpaired electrons in the F2 ion? Unpaired. These guys, sigmas have to be paired because you can only have 2 electrons. So that's paired, paired, paired. Paired because we have 2 of these pi's, right? And we've got 2 of these pi stars, but they go in according to Hund's rule like this and like this. So how many unpaired electrons? 2. So what does that say about this, the molecule's magnetism? It's paramagnetic because it unpaired electrons. So it will be drawn into a magnetic field. Okay, let's see. 19. Time, okay. Somebody scheduled a meeting I have to go to, butt up against the end of this class. So I'm racing the clock. Hybridization of the central atom in ClF2 plus. ClF2 plus. The implication here is that chlorine is central. And it's below and to the left means more metallic, so we put this one in the center. By the way, this is valence electrons is 7. 2 times 7 is 14, but we got to subtract 1 for that plus. All right. So that's 20 electrons. So we got a fluorine on either side. Okay, so that's 2, 4, 16 electrons we have to deal with. 2, 4, 6, 8, 10, 12. So we got 4 electrons left over. Okay, everybody's got an octet. And by the way, got to do that to make it official. Okay, what was the question? Hybridization of the central atom. Hybridization of the central atom is 1, 2, 3, 4. It's sp3. All right. Moving on to 21. This one's right better than the last one did. Which of the following does not contain at least one pi bond? Okay. In the interest of time, I'm going to drag out your memory and see if you remember. This one we've done before. B, CO2 is carbon in okay. Let's see, we've done I'm sure we've done C and D before. I don't know if you remember. C2H, how many? 4. And C2H6. This one's the easier one. CC, 1, 2, 3, 1, 2, 3, 6 hydrogens. This one is like that with 4 hydrogens and double bond there. Okay. This is ethane. This is ethene. Sometimes they call it ethylene. So you've heard of ethylene? Yeah. I think that's what they use to sterilize surgical instruments now. They don't autoclave them anymore. They put them in this device. It blows in ethylene, just goes straight through the package and kills all the bugs, and Bob's your uncle. H2CO, we haven't done that one yet, I don't think. So we'll take our time with this one. So we've got 2 there, 4 there, and 6 here. Right? That's 12 electrons, right? Carbon in the middle. We have an oxygen and 2 hydrogens. So that's 2, 4, 6. Got to use 6 more. 2, 4, 6. All we need to do is take 2 of those, make a double bond. Now we have 4 here. That's got its duet. That's got it. Okay. So at least 1 pi bond. Okay. That one does. That one does. And that one does. Oh, E. None of the above. Okay. So that doesn't work. We've got 3 that have at least 1 pi bond. Which of the following? Oh, does not contain. Careful. This one. That one does not contain a pi bond. All right. Let's see. Scroll, scroll, scroll. How about this one? 24. Complete the Lewis structure for the following molecule. Okay, they've given us a partial structure, which tells us what atoms are there, what bonds are formed, and then we just fill in what's missing. So we've got CH3, right? Then we have CH, and then we have another CH3 up here. And we have a C here with an oxygen and a C and a nitrogen. Okay. Now, if we do it in longhand, we would add up all the valence electrons. So we would have 1, 2, 3, 4, 5 carbons. 5 times 4 is 20, right? Then we would have 3, 6, 7. 7 times 1 is 7 for hydrogens. Then we have an oxygen, which has 6. And a nitrogen, which has 5. Yeah. 5 times 1. Add them all up. So that's 38. 38 electrons. Now, how many have we accounted for so far? Well, each one of these hydrogens is bonded with 2 electrons. Right? So that's 2, 4, 6, 8, 10, 12, 13, 14, 16, 18, 20, 22, 24. So we got 14 left. Where do they go? Well, work from the outside in. This already has an octet. That's already got an octet because it has 3 here and 1 there. This one has 3 and 1 there. Right? So we can put 6 of them there. That leaves 8, correct? And we can put 2, 3, 4, 5, 6. 6 of them there, which leaves 2. So where does the 2 go? Unless I counted them wrong. They're only supposed to be 36. 1, 2, 3, 4. 5 times 4 is 20. Ooh, where did I get this one? Not there. Where's 20? 6 times 1, 3, 6, 7. 7 times 1 is 7. for hydrogens. So this is for the carbons, this is hydrogens. Oxygen would be 6 times 1 equals 6. So that's for the oxygen, and this is for the nitrogen. So let's see. 12, 18, 23. So 1, 4, 5, 6, 7, 10, 11, 12, 13, 14. That's not right. 5 carbons. Oh, wait a minute. 1, 2, 3, 4. This should be 5. Oh, it is 5. 5 atoms times 4 electrons equals 20. Okay, so that's good. 6 for oxygen, and there's only 1 of them. Okay. And put these in the right order. 1 times 7. There we go. And then 1 times 5. There we go. 2, 8, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There we go. Okay, so this is 26, 7, 5. Now let's re-add them. 12, 18, 38. 5, 7, 6, 20. 26, 33, 38. Okay. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Right? 12 electrons. 2, 4, 6, 8, 10, 12. There we go. Okay. Now, let's make some double bonds where required. Octet's already good for this one, that one, that one. This one needs an octet. So we're going to pull 2 of those down there. And this one needs an octet. We're going to pull 2 of these here, here. There we go. That's our Lewis structure. So this molecule has how many sigma bonds? It has 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 sigmas, and how many pi's? 1, 2, 3. Okay, 13 and 3. If your instructor could count, we wouldn't take so long doing this. All right. Oops, skip that one. 26. We've got this skeletal structure. N, carbon, carbon, N. All right. What I'm seeing here is that's it. That's all there is to this molecule. So we've got 5, 10, and 8 is 18 electrons. So at 2, 4, 6, 12 electrons. 2, 4, 6, 8, 10, 12. Okay. So need another one. And we need there on that side. So how many pi bonds are there? 1, 2, 3, 4. I think this is hydrazine, which is a nasty material. You don't want to mess with it. The Nazis messed with it for their little rocket plane. I forget its number designation, but it killed a bunch of people on the ground trying to fill it up. Okay, 27. Right? Yeah, 27. Which of the following molecules contains the shortest carbon-carbon bond? Okay, so I'm going to have to fly through these and put their structures up here, but if you're faced with this one and you don't remember the structure, then you have to go through the Lewis procedure. C2H2, C2, well, we did a couple of these already, and C2H6, and then C2Cl4. Okay, this is acetylene. And this is our ethene. This is our ethane. And this is analogous to that one. It's going to have carbon-carbon double bond, but instead of hydrogens, we're going to have chlorines out here. Okay. Now, the strongest carbon-carbon bond here and the shortest carbon-carbon bond, when they put that C-C in there, they're not specifying that it has to be a single bond. That's just shorthand for a carbon-carbon bond. And we have different types of carbon-carbon bonds here. We have this one, and that one. This one is written the same. This is the strongest and the shortest right here, that triple bonded carbon. Now, if we were to leave that one out and say which one of these would be strongest, then you'd have to need a tiebreaker between this one and this one, the two double bonded ones. And the tiebreaker is the fact that chlorine is very electronegative. So it draws electrons away from that bond and weakens it. So that means this one would be the stronger one. Okay, that was 27. Um, 28. Okay, we're going to take a little break from the classroom recording, and I'm going to interject a solution to problem number 28. This is for Exam 7, Chapter 9 review. So let me scroll down to 28. There we go. Okay. During the class, if you had been there, or if you were there, you noticed that I was very confused. Somehow I got off on the wrong molecular orbital profile, and I couldn't get out of that trap. So I've had some time to think about it, and I'm going to inject this solution to number 28 so that it's the review is complete and correct. So number 28, when comparing diberyllium and dihydrogen, we have these 4 Roman numerals, 1 through 4, these possibilities, and we want to know which ones are true. All right, so if we have beryllium and hydrogen there, and we look at the possibilities here, Be2 is more stable because it contains both bonding and anti-bonding valence electrons. Okay, well, let's look at the molecular orbital configuration for these two, right? Hydrogen's easy. Right? It's just a sigma from the 1s's, and it has 2 electrons. That's it. No anti-bonding, just those 2. So its bond order is equal to 2 minus 0 divided by 2 equals 1. Okay? For beryllium, let's use just the valence electrons. So beryllium is in the second period. We're going to ignore the first two electrons and stick with the second. So normally what we do would be sigma 1s and sigma 1s star. But then when you get to the second period, you have sigma 2s and sigma 2s star. Okay. Now, if we're only counting valence electrons, beryllium is an alkaline earth. So it has 2 valence electrons for each beryllium. That means 4 electrons have to go into this molecular orbitals. So there are 2. Sigma can only hold 2, and sigma star can only hold 2. So the bond order is equal to 2 minus 2 divided by 2 equals 0. Okay? All right. So let's go to Roman numeral 1. Roman numeral 1 says Be2 is more stable. Is that true? It has a bond order of 0, whereas hydrogen has a bond order of 1. So the first part of that statement is false. Be2 is not more stable. Just because it contains both bonding and anti-bonding valence electrons doesn't make it more stable. The bond order tells you by comparison which one is more stable. So 1 is false. How about 2? H2 has a higher bond order than Be2. Yes, it does. Right? 1 is greater than 0. So that one is true. Okay. How about 3? Okay, Roman numeral 3. H2 is more stable because it only contains sigma 1s electrons. Okay, let's look at what they're trying to say. It only contains sigma 1s electrons. That means it has no anti-bonding electrons. Whereas Be2 does have anti-bonding electrons. That's the gist of that statement. H2 is more stable because it doesn't have any anti-bonding electrons. If it did, then it would have a reduced stability. And we see that with helium, right? He2 doesn't exist. Be2, I would guess, doesn't exist either. So 3, as far as it goes, is true. How about 4? Okay, let's see. Let's differentiate these here. How about 4? H2 is more stable because it is diamagnetic, whereas Be2 is paramagnetic. Well, let's see. Is it true? H2, is it diamagnetic? Yeah. Its electrons are paired, right? So it's diamagnetic. It's not drawn into a magnetic field. In fact, it's repelled by a magnetic field. But is Be2 paramagnetic? It has paired 2 and paired 2. It's not paramagnetic, right? So it has to be false. That statement is false. So we only have these 2, Roman numeral 2 and Roman numeral 3. And that's where I need to go back and change this back to where it was, because that's the truth. C is the correct answer for this problem. 29. Which of the following species is paramagnetic? A, B, C, D, and E. And we've got what? C2, O2, F2, and Li2. And then none. Okay, we're looking for paramagnetic. So we want unpaired electrons. Okay. Carbon. You know what? Since I'm going to give you the, come on. More, a little more. Come on. There we go. Carbon has sp mixing. And if we restrict ourselves to the valence electrons, which would be simpler, carbon only has 4 times 2 is 8. So let's do that. 8 valence electrons. Oxygen has 612. F2 has 14. Lithium only has 2 valence electrons. Okay. Oxygen will have no sp mixing. So if we go to the second level, then we're going to have sigma 2s and sigma star 2s. Then no mixing would be sigma 2p, pi 2p. That probably is enough. 2, 4, 6. Nope, one more. And then pi 2p star. There we go. So that's no mixing. Carbon's going to have mixing. Fluorine has no mixing. So we can use the same sequence for fluorine. And lithium will have mixing. So carbon and lithium are going to have mixing. So this is going to be 2s. This is going to be sigma star 2s. This is going to be pi 2p and sigma 2p. 4. That's enough. Lithium won't even need that much. That's all lithium needs. Okay, so let's populate these with electrons. Carbon has 8, so that's 2, 4, and 4 is 8. Okay, oxygen has 2, 4, 6, and 4 is 10, and then 2 here. And then fluorine has 2, 4, 6, 10, and 4 more. It is 14. And this one has 2. These are paired, 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 unpaired, and paired. This one is paramagnetic. The rest of them are diamagnetic. Okay? So oxygen is the only one that's, let's go back up. And here we go, 29. Yeah, oxygen is the only paramagnetic one in there. All right, 30. For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? Okay. Adding or subtracting electrons in the molecular orbital model, the effect that it has on the bond order depends on whether it's happening with a bonding or an anti-bonding orbital. So we need to do B2, C2, B2O2, excuse me. 30, excuse me, I'm in the wrong one. I had it right the first time. B2, C2, P2, and F2. Okay. I wish I'd have kept those others up on the board now. So, no mixing, 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 C2 mixing, and boron mixing. So the no mixing is going to be sigma 2s, sigma star 2s, and no mixing would be sigma 2p, pi 2p, pi star 2p, and sigma star 2p. And then this one is in the third group, the third period. So instead of 2, we're going to have 3. And this has mixing, so it's going to be sigma 3s and sigma star 3s. And pi 3p and pi 3p, and then pi star 3p and sigma star 3p. Then carbon is going to be, let's see, sigma star 2s, 2s. And then with mixing, it's going to be pi 2p and sigma 2p. I don't know if we're going to need, yeah, we are going to need more for, no, not for carbon. And boron is going to be mixing also, so it'd be 2s sigma star. We may not need all of these. Okay, valence electrons. Boron is 6 valence electrons. Carbon would be 4 times 8. Phosphorus would be the same as nitrogen. It'd be 5 times 2 is 10. These are electrons. And then fluorine is 14. So 2, 4, 6, 10, and 4. So there's fluorine. Phosphorus is going to have 10, so it's 2, 4, 8, 10. That's it. Okay, carbon is 4. No, 8. 1, 2, 3, 4. Yeah, 8. 2, 4, 8. Correct? And boron is 6. 2, 4, 6. Okay, now the question is, which of the following is, let's see, 30, excuse me. For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? So if we add an electron, where's it going to go? Let's see, bond order. Calculated bond order. If we add an electron here, it's going to go there. So the bond order is going to increase because you're adding to a bonding orbital. Add 1 here. Oh, we can't. So we got to go to sigma 2p, right? Yeah. Add 1 here. That also increases because we add to a bonding order or orbital. Here, oh, we have to add, let's see, this is going to be pi star 3p. Add 1 here, you're adding it to an anti-bonding that would decrease. And here we've got no mixing. That would decrease. So 2 of them are going to decrease. Two will decrease, two will increase. Okay. Let's see. I'll tell you what. I'm gonna leave those up here in case I need them again. That takes a lot of time to draw those things out. Let's look at 31. Which of the following has the largest bond order? All right, let's draw the neutral dinitrogen, well, they're in order. A, B, C, D, and E. So we got N2, we have N2 with 1 minus and N2 with 2 minus. And then we have an N2 with a plus and an N2 with a 2 plus. So if we take nitrogen, which we'll have mixing. And let's see, this neutral has 10 valence electrons. So we've got a 2, excuse me, a sigma, 2p, a sigma, we have a sigma star. Wait a minute. Yeah, sigma star 2p. Then we have a pi 2p and a sigma 2p. That should be enough. 2, 4, 8, and 10. There we go. Okay. So that gives us a bond order here. So where is this? 30, 31. I'll put the bond orders over here. So this gives us a bond order of 3, right? 4, 5, 6, 7, 8 minus 2 is 6 divided by 2 is 3. Okay. So if we add an electron, where's it going? Well, it's going to go out here with a pi star 2p. We're going to decrease the bond order by a half. If you add 1 electron divided by 2, that decreases it by a half because we're adding it to an anti-bonding orbital. So this one's 2.5. If we do 2, we still have to add it to that anti-bonding. That decreases it by 1. Now, if we subtract, we're subtracting from a bonding orbital, which will also decrease the order by a half. So now it's 2.5. And if we subtract 2 electrons, we'll go to 2. So the largest bonding order is the neutral N2. If we add or subtract 1 or 2 electrons, we're weakening that bond, weakening that molecule. Okay. Order the following from shortest to longest bond. All right. Is nitrogen in there? Yeah, nitrogen's in there. Okay. So let's do this. Keep that nitrogen. And we don't have any ions, so we can wipe those out. We got that nitrogen. And now we're working on 32. Okay. Let's see. We've got nitrogen, diboron. We've got nitrogen to select from, and we have hydrogen and dicarbon. And all we have to do now is hydrogen to compare these. So it's got 2 electrons and it's just like this. Okay, so we can do away with these. Well, I better not. I might need them later. So we want to put these in order from shortest to longest bond. Okay, first thing we would do is calculate the bond order. And then we would apply some other mitigating circumstances. So this one would have 4 minus 2 is 2 divided by 1 is 1. So this is a bond order of 1. This is, I don't need that one. This is 4, 5, 6 minus 2 is 4 divided by 2 is a double bond, right? And this one is 1, bond order equals 1, and this is a bond order equals 3. Okay, the shortest to longest. Definitely that triple bond should be the shortest, except size of the atom. Nitrogen compared to hydrogen is huge. So even though it has a triple bond, it's not going to be able to get close enough. When you put 2 protons together with 1 bond between them, this is the shortest one. Okay. Then you get the rest of them you can put in that order. N2, a triple bond is shorter, and then C2, and then B2. Okay. That's the tricky part right there. When we're just talking about the shortest to longest bond. I think that's why I stuck that one in there. Oh, I am out of time. Let's see. If we do CO, that's a heteroatomic molecule. Yeah, I'm going to stay and finish this thing up. I'll miss the meeting. That's too bad. It's a voluntary committee anyway, not mandatory. What did I say? 39. All right. CO. All right. Are we given any instructions in the molecular orbital description of carbon monoxide? No, we're not. Okay. I think this has sp mixing. Okay. And since they're in the same period and they're fairly close together, I don't think we're going to get any more serious changes than this I2P and sigma 2P. Okay, how many electrons for carbon monoxide? 4 and 5 is 9. Wait a minute. No, 6. 4 and 6 is 10. 10 electrons. So 2, 4, 8, and 10. Okay. So which ones of these? I guess we're looking for the true statement. And this should be none or true. Okay, what about the first one? The highest energy electrons occupy anti-bonding orbitals. Nope. Bonding orbitals. 5 molecular orbitals contain electrons. 1, 2, 3, 4. Nope. There are 2 unpaired electrons. Nope, these are all paired. Paired. All right, you can have 4 in this one because there are 2 levels. That's false. Last chance, the bond order is 3. Okay, let's calculate that. So it's 2, 6, 7, 8. minus 2 over 3. Excuse me, 2. I was thinking ahead of myself. That was true. Bond order is 3. All right, 41. Go. Which of the following, move this thing out of my way. Which of the following statements about CO3 2- ion is false? CO3 2-. Let's see what kind of statements there are. The orbitals on the carbon atom are sp2 hybridized. The ion is expected to be diamagnetic. CO bonds are different lengths. The ion has total 24 electrons. Okay, so we've got a mix of molecular orbital and model and the valence bond. So and E. Okay, the first one has to do with orbitals on the carbon atom are sp2 hybridized. So we got to draw our one carbon is 4, 3 times 6 is 18 plus 2 for the charge, right? So that's 24 electrons. So carbon, 3 oxygens, that's 2, 4, 6 is 18 left over. 2, 4, 6, 8, 10, 12, 14, 16, 18. That's it. Okay, so this is one where you can, to answer this question, we don't need to concern ourselves with hybridization. So we just say, take 2 off of one of these oxygens. Now that carbon has an octet and it has 3 groups, which means sp2 hybrid. Okay, the carbon is sp2 hybridized, A. Which is the following? Wait a minute. The orbitals on the carbon atom are sp2 hybridized. A is true. If I did that right, did I do it right? 4, 3 times 6 is 18 plus 2, that's 24. 2, 4, 6, yeah, 6. That's right, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. And this has a 2- charge. Yeah, that's sp2 hybridized. So there's something wrong with that one too, because we have, this is a possibility. That's true. How about B? The ion is expected to be diamagnetic. Okay, this one's going to be a problem. Right, if we have carbon and oxygen, are we going to say this is sp mixing or not? It's difficult. Let's see, what did I say? Unpaired electrons. Well, if we look at this, of course, there are no unpaired electrons, but we know that the molecular orbital model may not agree with that. Okay, so if we were to draw this out as a molecular orbital, then we would have to, we would say, assuming sp mixing. So this would be 2s sigma star 2s sigma 2p pi 2p pi star 2p sigma star 2p. I'm not sure we got enough orbitals for all the electrons. These are only valence electrons, so we have 24, 2, 4, 6, 10, 14, 16. So we've used up 16. We need 8 more. Yeah, we need 8 more. So what goes from here? Now we got to go up to the 3. So the sigma 3s, right? Am I barking up the wrong tree? That's all we've got there. We have to go 3. Sigma 3s and sigma star 3s. So we need 8 more, 2, 4. And then I assume we still have mixing. So we have pi 3p. That would give us 4 more. So 4, 8, 10, 20, 6. Well, we only need 24. That says that this molecule should be paramagnetic. Okay, that's a bad question, because I don't think we have the expertise to answer that B part. Yeah, I think that one ought to be discarded. If it slips into the exam, I've already created the exam and I haven't checked to see if that one's in there. If that one's in there, then we need to toss it. That's beyond our expertise, because we're starting to get too many atomic orbitals mixed up into making molecular orbitals, and we haven't gone that far yet. We haven't made it past diatomics. Okay, 42. Not that it can't be done, it's just we can't do it. How many electrons are involved in pi bonding in benzene? Okay, the best way to answer that one is to draw it the traditional way. Oops. Like that. So the electrons involved in pi bonding, we've got 1, 2, 3 pi's times 2 is 6. 6 electrons are involved in pi bonding. Let's see, 45. Should have kept that. I didn't see this one coming. Which of the following has the highest bond dissociation energy? Well, N2, right? Because we know we've done the bond orders, and the highest bond order is N2, neutral dinitrogen. The others are weaker, so they have lower bond dissociation energies. So A is obviously the right choice there. There's nothing funky about that one. 47. Which of the following molecules or ions does not contain a central atom with D2sp3 hybridization? All right. In this case, we've got some drawing to do. Let's spread them out this direction. E, all these contain D2sp3. So E would be all. All right, first one is xenon pentafluoride ion. Xenon pentafluoride ion. And then we have IF4. That's kind of a small, there's a negative sign next to that one. IF4 minus. This one's SF6. And this one's SEF5 minus. Okay, we're back to the valence bond theory. So, how many valence electrons do we have here? 8. 5 times 7 is 35. 8 plus 35 minus 1. Okay, so that's 42. 42 electrons. Yeah. This one has 5 times, let's see, 4 plus 1 is 5 times 7 is 35 plus 1 is 36. This one has 42 and sulfur has 6. So this is 48 electrons. And this one's like sulfur. Yeah. So it's going to be 5 times 7 is 35 plus 6. 35 plus 6 is 41 plus 1 is 42. Okay, now we can draw their structures. Xenon with 1, 2, 3, 4, 5 fluorines. Okay, 2, 4, 6, 8, 10. That means 32 left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we have 2 more right here. That's 1, 2, 3, 4, 5, 6 groups. This is D2SP3. Okay, we have iodine and 4 fluorines. So that's 2, 4, 6, 8 is 28 electrons left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. So that's 4 more left. 1, 1, 1, 1. 1, 2, 3, 4, 5, 6. This is D2SP3. S in the middle with fluorines around. We've used 2, 4, 6, 8, 10, 12. So that's 36 electrons left. 2, 4, 6. 6 times 6 is 36. Used them all up. So this is D2SP3, right? 6 groups. And this one, selenium with 1, 2, 3, 4, 5 chlorines. 2, 4, 6, 8, 10. 32 left over. Oops, dropped the cap. So 2, 4, 6. 6 times 5 is 30. That leaves 2 left over. This is also D2SP3. All of them. So ease your answer. That's a Lewis dot mess. Let's see, those are fill in the blanks. That's just memorization. I hadn't had marked them anyway. How about, what's the next one? Okay. Let's fill in this chart. Okay, number 60. And we have 1, 2, 3, 4 across and 1, 2, 3, 4, 5 down. So we have 4 across. Right? Yeah, 4 across. And 5 down. There's 1, 2, 3, 4, and 5. Okay. All right, so this is empty. This is molecule A, B, and C. And here we have electronic geometry. Here we have hybridization. Here we have bond angles. And here we have an example. Okay, so what are we given? That's what we're looking for. ABC molecule A has a hybridization of sp3. So A has sp3. We're given that. Okay, we're not given anything else except based upon that. All right, so let me see. Let me get a different color here. Won't stand out. Purple. Let's try purple. All right. So molecule B has 2 more effective pairs around the central atom than molecule A. So if it has 2 more, B should be D2sp3. Right? Okay. Molecule C consists of 1 sigma bond and 2 pi bonds. All right. How do you get a sigma, 1 sigmas and 2 pi's? The only way that you can get a sigma and a pi is if you have, there's your sigma, and you can't put pi's anywhere else. So they have to go here. That means it's triple bonded, right? And with, that means it's a linear molecule, and any hybridization must be sp. Okay, give the electronic, okay, now we can work from this. Electronic geometry here is going to be tetrahedral. This one's going to be octahedral. This one's going to be linear. Okay. Bond angles in a tetrahedron, 109.5 degrees. How about octahedral? Sometimes I have to draw it out. If you have something in the middle, and then you have something here and here, then you can have bond angle of 180 this way or 90 degrees everywhere else. If we're talking about the bonds, right, there's right angles everywhere, except for if you have something here and here. So this is potential. You may not have that if one of these is a lone pair, but it has the potential of 90 and 180 degrees. Okay. How about linear? Only one possibility, 180 degrees. Now, examples. Methane's a good one for this one, right? CH4 or carbon tetrachloride would be a good one. A tetrahedral, actually, you could use ammonia because it has 3 attached hydrogens in 1 lone pair, which would still give it that electronic geometry. Let's see, octahedral. We just did one before. Excuse me, SF6. That's a good one. And linear, I don't know, N2 or carbon monoxide. Those would be good examples of linears. Okay. Right. Let's see. Trying out. Let's see, got anything else? Oh. Let's see. Draw a molecular orbital diagram of O2 and N2 using molecular orbital theory. Explain why the removal of 1 electron in O2 strengthens the bond, removal of 1 electron in N2 weakens the bond. Okay, you're going to have access to that chart with the molecular orbitals for each one of those. All right, if we go down here, Actually, we have two of them. So here's N2, and you just have to read off the side, or you can go down to this one. There's N2 and there's O2. Right? So it's just a simple matter of copying, but then explain. Okay, the further explanation is why removing one electron from O2 strengthens the bond, removing from N2 weakens it. So you see where the electrons are. If you remove one from, let's see, the left one is N2. Remove one from N2, it's from a bonding orbital. So that decreases the bond order. If you remove one from oxygen, it's from an anti-bonding orbital. That increases the bond order. And just put that in your own words. I think that's it. Yep, that's it.